Right now, a machine the size of a small car is moving through space 15 billion miles away. Built in the 1970s, running on less power than a refrigerator light bulb, it is the only human-made object to have crossed the boundary separating our solar system from the rest of the galaxy. When it finally crossed that boundary, scientists expected what their models had been promising for decades: clean edges, predictable fields, a boundary that behaved like a boundary. Instead, almost every major prediction was wrong. The magnetic field refused to rotate, the temperature was too high, the heliosphere turned out to breathe. The shape of everything we call home was something nobody had modeled. What exactly did Voyager find out there? There is a signal traveling through space right now, aimed at Earth, and it has been traveling for more than 22 hours. It moves at the speed of light, which means it is covering roughly 670 million miles every hour, and it has still been in transit for more than a day. The machine that sent it is currently more than 15 billion miles from our planet, which means the distance between that machine and Earth is so large that light itself, the fastest thing in the universe, needs the better part of a day to cover it. Most people, when they hear numbers like this, feel the numbers but don't feel the scale. So consider it from a human perspective. If you wanted to drive to where Voyager 1 is right now, at a perfectly steady highway speed, never stopping for gas or sleep or food, it would take you about 17 million years. The first humans hadn't appeared on Earth yet when you would have needed to set out. The oldest stone tools we know of are only about 3.5 million years old. You would have needed to leave before any human hand ever shaped any object on this planet, and you still wouldn't have arrived. Now consider that the machine we sent there runs on the heat of decaying metal, that its engineers did their calculations on paper, by hand, using mechanical pencils and slide rules and early computers with less processing power than a modern digital watch, that it weighs less than 1,000 pounds, that it carries no humans, no human immune system, no human ability to repair itself or make decisions in real time. It is a collection of circuits and sensors and antennas from the 1970s rolling through the interstellar medium at 38,000 miles per hour, and it has been doing this without a single break for nearly 5 decades. It is called Voyager 1. It is the most distant object humanity has ever built, and when it crossed the boundary of the solar system and entered interstellar space, the data it sent home did not confirm what physicists expected. It contradicted nearly all of it. The boundaries were in the wrong places. The temperatures were wrong. The magnetic fields refused to behave as decades of theory said they should. The shape of the entire heliosphere, the bubble of solar wind that surrounds our star and all its planets, turned out to be something that no model had correctly predicted. Every major feature of the solar boundary was, in some significant way, not what it was supposed to be. What follows is the story of what Voyager actually found out there. It is also a story about the limits of modeling, the value of actually going to look at something, and what it means for our understanding of this corner of the galaxy when the universe refuses to cooperate with our equations. In 1965, a young scientist named Gary Flandreau was working at NASA's Jet Propulsion Laboratory when he noticed something that most people would have overlooked. He was doing orbital calculations for potential outer planet missions, and he saw it. The outer planets were going to line up, not in some mystical sense, but in a purely geometric one. Jupiter, Saturn, Uranus, and Neptune were going to be positioned over the course of the 1970s and 1980s in a way that would allow a single spacecraft to fly from one to the next, using each planet's gravity to redirect and accelerate toward the next stop on the list. This kind of alignment is rare. It happens roughly once every 176 years. The previous time it happened, Mozart had just been born. The next time it will happen, nearly everyone alive today will be dead. Flandreau's insight was simple and enormous. If you launched a spacecraft in the late 1970s, You could visit all 4 of the outer gas giants in a single mission without carrying the fuel to reach each one directly. Gravity was free. You just had to aim correctly, and aim soon. The project that followed was originally called the Planetary Grand Tour. Over time, budget pressures and engineering compromises shaped it into the Voyager program. 2 spacecraft instead of 4, visiting Jupiter and Saturn both, with Voyager 2 continuing to Uranus and Neptune. The ambition was barely diminished. This was still the most geographically ambitious scientific mission in history, visiting more planetary bodies in a single sweep than any probe had ever attempted. But the planets were always just the beginning. The real destination was the edge of the solar system itself. Both probes were built with enough power, enough scientific instrumentation, and enough engineering margin to survive both the planetary encounters and the decades-long coast that would follow, outward through the heliosphere toward whatever waited at the boundary between our solar system and interstellar space. Nobody knew exactly what that boundary looked like. Nobody had been there. But theories had been written, models had been built, and a picture existed of what the edge should be. That picture was about to be tested, for the first time, by machines actually going there. Voyager 1 launched on September 5, 1977. Its twin, Voyager 2, launched 16 days earlier, on August 20, but the 2 probes were placed on different trajectories, and Voyager 1's faster, more direct path meant it overtook its sibling quickly. Each probe carried 11 scientific instruments: cameras, spectrometers for measuring atmospheric composition, magnetometers for tracking magnetic fields, plasma science instruments for measuring the solar wind, low-energy charged particle instruments for tracking energetic particles, cosmic ray instruments for high-energy particles from the galaxy, and plasma wave receivers for detecting oscillations in the local plasma. Each probe also carried 3 radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium into electricity. They produce about 470 watts at launch. The output drops by roughly 4 watts per year. The math of their eventual silence was built in from the beginning. Each probe also carried a golden record, a 1-2-inch gold-plated copper disc, encoded with sounds, images, and greetings from Earth. Natural sounds, rain, wind, surf, animals, music from many cultures, spoken greetings in 55 languages, images of humans, of our planet's geography, of our science and our art. A diagram showing the probe's origin point in the galaxy, using the timing of known pulsars as a cosmic coordinate system. The records were a message to whoever or whatever might someday find one of these machines. They were also a statement of intent. When humanity sends a machine to the stars, it brings something of its soul along for the ride. The records were, in practical terms, entirely redundant. The chances of any intelligent finder encountering either probe over any reasonable time frame are essentially 0. The galaxy is far too large, and the probes are far too small. But the records were not really about practical probability. They were about choosing, at the moment of departure, to carry something more than data. They were about saying, "We were here, and this is who we were." The scientific data was another matter entirely. That data was meant to be found, meant to be received, and meant to change what we knew. And from the very first planetary encounters, it did. Voyager 1 flew past Jupiter in March 1979 and delivered a set of revelations that astonished scientists. Io, the innermost of the 4 large Galilean moons, was volcanically active. This had been predicted by a paper published a few weeks before the flyby, based on gravitational heating calculations, but nobody was quite prepared for the actual images of eruption plumes rising above Io's surface against the black sky. It was the first active volcanic system ever directly observed on a body other than Earth. The Jovian system also revealed a ring of particles orbiting the planet's equator, previously unknown. The radiation environment in Jupiter's inner magnetosphere was far more intense and complex than anyone had fully anticipated. The magnetosphere itself was enormous, so large that if it were visible from Earth, it would appear several times larger than the full moon. Saturn was next. Voyager 1 reached it in November 1980, and the ring system revealed itself to be almost incomprehensibly complex. Thousands of individual ringlets, with gaps that weren't fully explained by known moons, with waves and braids and structures that seemed to defy the gravitational models available at the time. The moon Titan, which Voyager 1 made its primary target, was wrapped in an orange-brown smog so thick that the surface was invisible, even at close range. The atmosphere turned out to be primarily nitrogen, the same gas that makes up most of Earth's atmosphere, but at temperatures cold enough to liquefy it. Scientists suspected Titan might have lakes or seas of liquid methane on its surface, a prediction that wouldn't be confirmed until decades later. The Titan flyby, as beautiful and scientifically rich as it was, sealed Voyager 1's trajectory into a shape that pointed it northward, out of the ecliptic plane, and directly toward the upper reaches of the heliosphere. From the moment the gravitational assist from the Titan encounter was complete, Voyager 1 was done with the solar system's planets. Its cameras were largely powered down to save energy. The scientific focus shifted to the invisible environments of particles and fields, and the probe began its long, dark, silent coast toward the boundary of everything we called home. The boundary it was heading for had a theoretical description that physicists had been refining for decades. The key concept was the solar wind, and understanding it is essential to understanding everything that came after. The star at the center of our solar system, like all stars, continuously ejects material from its outer layers, electrons and protons mostly, with some heavier ions mixed in, streaming outward at speeds ranging from about 250 miles per second in quiet periods to well over 500 miles per second during storms. These particles carry with them the magnetic field of the star's outer layers, wound into a spiral pattern by the star's rotation, filling the entire heliosphere with an outward-flowing, magnetized wind. The solar wind doesn't travel forever unchanged. As it moves outward, it thins and slows due to simple geometry. The same amount of mass is spreading across an ever larger sphere, so the density and energy per unit volume drop with the square of the distance. At some point, the solar wind has to stop. Outside the heliosphere is the interstellar medium, the thin plasma and gas that fills the galaxy between star systems. The interstellar medium has its own pressure, its own magnetic field, its own slow drift of neutral atoms and charged particles. The solar wind's expansion must eventually balance against the pressure from the interstellar medium, and where balance is reached, the solar wind stops flowing outward. The theoretical picture that physicists built around this confrontation had elegant geometry. A bow shock would form in the interstellar medium ahead of the heliosphere, like the shock wave ahead of a supersonic jet, created by the heliosphere moving through the interstellar medium at high speed. Just inside that bow shock, the solar wind would hit the termination shock, the inner boundary where the supersonic solar wind became subsonic, slowing down and heating up dramatically as its kinetic energy was converted to thermal energy. The slowed, hot material between the termination shock and the outer boundary of the heliosphere was called the heliosheath, and the outer boundary itself, where solar material stopped and interstellar material began, was the heliopause. All these features were expected to be organized roughly concentrically, like layers of an onion centered on the star. The heliosphere as a whole was drawn as a sphere, or slightly elongated by the heliosphere's motion through the interstellar medium, with the nose pointing into the interstellar wind direction and a long tail extending downstream. The overall picture fit on a page. It was coherent, it was mathematically defensible, and it was, in almost every important respect, wrong. That wrongness would only become visible when the probes actually got there. First, they had to survive the decades-long crossing. The Voyager interstellar mission, as the long-range scientific phase of the program was officially called, began in earnest after the last planetary encounters. For Voyager 1, That was after Saturn in 1980. For Voyager 2, it was after Neptune in 1989. Both probes were pointed outward, their particle and field instruments running continuously, their data streams flowing back to Earth at the speed of light across distances that grew longer every day. Engineering the mission through these decades required constant attention and ongoing creativity. The power output from the radioisotope generators dropped every year, which meant instruments had to be shut off in a specific order, with the most important science measurements prioritized for last. Heaters that kept sensitive electronics warm in the extreme cold of space had to be evaluated against their power cost and eventually sacrificed to keep the science instruments running. The computers aboard the probes were programmable from Earth, and mission controllers uploaded new software multiple times over the decades to improve efficiency, fix bugs, and adapt the instruments to the changing environment they were measuring. The cosmic ray instruments ran continuously and tracked the steady influx of high-energy particles from the galaxy, building a long-term picture of how the heliosphere filtered and blocked these particles at different distances. The magnetic field instruments measured the direction and strength of the solar magnetic field as the star's activity cycle waxed and waned year after year, sending ripples and waves outward through the heliosphere. The plasma wave instruments listened for oscillations in the local plasma that could reveal its density and temperature even without a direct plasma measurement. All this data was building a picture of the outer heliosphere that was partially satisfying and partially unsettling. The general structure was roughly as expected. The solar wind weakened with distance. The magnetic field shifted in response to the star's rotation cycle. Cosmic ray counts rose slowly as the probe moved farther from the shielding center of the heliosphere, but the details didn't quite fit. The outer heliosphere was more structured, more complex, more variable than the smooth, gradual models had predicted. Something was happening out there that the models weren't capturing. The first definitive confrontation with the boundary came in December 2004. Voyager 1 was roughly 94 astronomical units from the star, which is about 8.7 billion miles. 1 astronomical unit is roughly 93 million miles, the distance between Earth and the star. So 94 astronomical units is 94 times that distance. The probe had been traveling for 27 years to get there, and the termination shock was finally close. The crossing was confirmed by multiple instruments over several days. The solar wind slowed sharply. The magnetic field data shifted in ways consistent with a shock boundary. Cosmic ray intensities changed. The heliosheath was on the other side. Voyager 1 had crossed the first major boundary of the heliosphere, and the proton heating problem was immediately apparent. The solar wind protons should have heated dramatically at the termination shock. When you slow supersonic flow to subsonic speeds, kinetic energy converts to thermal energy, and the theoretical prediction for the proton temperature jump was about a factor of 30. What the instruments showed was a temperature increase of roughly a factor of 3. The protons were cold. The energy that should have heated them had gone somewhere else. The resolution took years to assemble. Pickup ions were the key. These are atoms from the interstellar medium that drift into the heliosphere, get ionized by the star's ultraviolet light or by interactions with solar wind particles, and then get swept up by the solar wind's magnetic field. Because they start from rest rather than from the wind's outward velocity, they carry their energy in a way that doesn't show up clearly in the proton temperature. At the termination shock, pickup ions absorb the energy that protons should have received. The models had treated pickup ions as a minor correction. They weren't. They were a major physical component of the outer heliosphere, and their behavior at the termination shock was nothing like what the simplified models had assumed. The lesson was clear. The outer heliosphere is not a simple place, and the lesson would be repeated many times before the probes finished their work. The second probe's crossing confirmed and extended the first. Voyager 2 reached the termination shock in August 2007 at roughly 84 astronomical units. The difference between 84 and 94 astronomical units is not experimental uncertainty. It is a genuine difference in where the termination shock is, in 2 different directions from the star, sampled by 2 separate probes 3 years apart. 10 astronomical units is about 930 million miles. The termination shock was measurably closer to the star in the direction Voyager 2 was traveling than in the direction Voyager 1 had taken. The heliosphere was not a sphere. The textbook diagram was wrong. The real boundary was being pushed inward from one side, likely by the pressure of the interstellar magnetic field pressing on the heliosphere asymmetrically. Where the field exerted more pressure, the heliosphere was compressed. Where it exerted less, the heliosphere expanded farther out. The heliosphere was a lopsided bubble in a magnetic environment that was pushing on it from outside, and the 2 crossing distances, 84 and 94 astronomical units, were the first direct proof of that asymmetry. The termination shock wasn't just in the wrong place, it was doing the wrong things, and the heliosheath it led into was about to produce the most unexpected physics yet. Inside the heliosheath, both probes began measuring magnetic field behavior that had no place in any pre-Voyager model. The heliosheath was supposed to be a relatively simple buffer zone of hot, turbulent, slowed solar wind plasma. The magnetic field was expected to be somewhat disordered from the turbulence of the termination shock crossing, but gradually smoothing out as alternating sectors of solar magnetic polarity mixed together and cancelled through magnetic reconnection. By the time you reach the outer edge of the heliosheath, the magnetic field should have been fairly uniform. Instead, the sector structure persisted. The heliospheric current sheet, the boundary between alternating sectors of opposite magnetic polarity, was found deep in the heliosheath, far beyond where models said it should have dissolved. The magnetic organization of the solar wind was lasting much longer than expected. The heliosheath was not well mixed. It was structured, layered, and organized in ways the models hadn't predicted. Deeper into the heliosheath, the magnetic field data revealed something even more striking. The field was forming closed loops, bubbles, isolated regions where the field lines had reconnected and formed self-contained magnetic islands, disconnected from the main solar magnetic field, drifting through the heliosheath like bubbles in foam. Scientists analyzing the data called it exactly that, magnetic foam. The outer heliosphere was filled with it. Each bubble was roughly an astronomical unit, or more in size, about 93 million miles across. The foam covered a significant fraction of the heliosheath volume, and every calculation that had assumed a relatively clean, continuous magnetic field through the heliosheath was invalidated. Cosmic ray transport through the heliosheath, the mixing of interstellar and solar particles, the exchange of energy between the heliosphere and the interstellar medium, all of these depended on what the magnetic field was doing, and what it was doing was something nobody had modeled. Both probes continued outward. The data kept challenging the models, and the boundary itself, the heliopause, was still ahead. Around 2010, Voyager 1's instruments registered a shift that was more dramatic than anything that had come before. The solar wind, which had been slowing for years as the probe pushed deeper into the heliosheath, stopped moving outward. The outward velocity component fell to essentially zero. The probe was in what scientists would call the stagnation region, a zone where the solar wind's outward pressure was exactly balanced by the inward pressure of the interstellar medium from the other side, creating a standstill. The solar wind hadn't disappeared. The plasma was still there, still detectable, still warm. It had simply stopped going anywhere. The flow that had been blowing outward continuously from the star since well before life appeared on Earth had, at this one location in this one small slice of the heliosphere, come to a complete halt. Simultaneously, the magnetic field intensity rose. The field lines were piling up at the stagnation boundary, compressed by the opposing pressure from outside, and galactic cosmic rays were flooding into the stagnation region at higher rates. The heliosphere's outer magnetic defenses were clearly weakening. High-energy particles from the galaxy that normally couldn't penetrate this deep were getting through in increasing numbers. The heliopause was close, and it was already making its presence felt in the physics of the region ahead of it. The stagnation region lasted for roughly 2 years before Voyager 1 began moving through a clear transition into interstellar space. But the transition, when it finally came, didn't look like anything the models had predicted. In the stagnation region, the data told a story of two systems meeting without mixing. The solar wind plasma was trapped, going nowhere, piling up against an invisible wall. The magnetic field was building in intensity, as if something was pressing on it from the outside, compressing it like a spring being wound tighter and tighter. And the cosmic ray counts from the galaxy were rising steadily, reaching deeper into the heliosphere than they should have been able to penetrate at that depth. Galactic cosmic rays are not the same thing as the light or radio waves we usually think of when we think about radiation from space. They are particles, mostly protons, but also heavier atomic nuclei, stripped bare of their electrons. They are moving at speeds approaching the speed of light. They were born in violence. Supernovae, the enormous explosions of massive stars at the ends of their lives, accelerate particles to incredible energies in the shock waves that ring out from the explosion. Other sources include pulsars, active galactic nuclei, and other energetic events scattered throughout the galaxy. These particles travel through the galaxy for millions of years, bouncing off magnetic fields, ricocheting off gas clouds, before eventually reaching our corner of space. The heliosphere partially blocks them. The magnetic field carried in the solar wind deflects lower energy cosmic rays, preventing them from penetrating too deeply. Inside the heliosphere, the cosmic ray spectrum is incomplete, filtered, depleted at the low energy end by the solar wind's magnetic defenses. The farther you travel from the center of the heliosphere, the closer you get to the heliopause, the weaker those defenses become, and the more cosmic rays can get through. In the stagnation region, Voyager 1's cosmic ray instruments were detecting particles that normally would have been blocked at greater depths. The boundary was leaking. The heliosphere's shield was fraying at its edges. What made this observation so striking was the timing. The probe hadn't crossed the heliopause yet. It was still technically inside the heliosphere, still in the domain of the solar wind, still surrounded by solar plasma. But the interstellar medium was already influencing the physics of the region, pressing inward, leaking its particles through the increasingly compressed and fragile outer boundary of the heliosphere. The cosmic ray surge was a warning signal, a ghost of the crossing that was coming. For scientists watching the data, this created a fascinating problem. How would they know when the crossing actually happened? The stagnation region made the boundary seem gradual rather than sharp. The cosmic rays were already rising before the crossing. The magnetic field was already changing. Where did the heliosphere end? At what precise moment would the probe leave the domain of the star and enter the interstellar medium? There was no line painted in space. There was no moment when an instrument would simply flip from one reading to another. The data would have to be interpreted, and interpretation would require time. August 25, 2012 is the date that has been retrospectively identified as the heliopause crossing. But at the time, scientists weren't sure. The probe crossed some kind of boundary on that date, and the magnetic field data and particle data both shifted in significant ways. The magnetic field intensified. The low-energy particle populations changed. Anomalous cosmic rays began dropping, but the field direction barely rotated. The models said the magnetic field should swing dramatically at the heliopause, rotating from the direction of the solar magnetic field to the direction of the interstellar magnetic field. The solar magnetic field and the interstellar magnetic field were supposed to be running at a significant angle to each other, roughly 90 degrees in some models. If the probe had crossed the heliopause, the magnetic field direction should have jumped by that much. It didn't. The magnetic field outside the crossing looked almost identical in direction to the field inside. The rotation was minor. If you were looking for a 90-degree swing in the field direction as the signature of the heliopause crossing, you wouldn't see it in August 2012. Scientists spent months debating what had actually happened. Had the probe crossed the heliopause? Or was it in some new, unmodeled region that lay between the heliosheath and true interstellar space? But the magnetic field still hadn't rotated. And when scientists finally confirmed the crossing months later, that non-rotation was the most unsettling finding of all. The magnetic field non-rotation was not a measurement error, and it was not ambiguous. The magnetometers on Voyager 1 had been some of the most reliable instruments on the probe, running continuously and producing high-quality data for decades. The field directions they recorded inside the heliosheath and outside the heliopause were carefully analyzed, verified, and cross-checked against every possible source of instrumental error. The findings stood. The interstellar magnetic field just outside the heliopause of our solar system runs in nearly the same direction as the solar magnetic field just inside it. This mattered for a reason that goes beyond the immediate physics of the point: crossing. The direction of the interstellar magnetic field outside the heliosphere was something that scientists had been estimating from a distance for decades, using indirect methods. The polarization of starlight, for example, reflects the alignment of dust grains in space, which in turn reflects the orientation of the magnetic field those grains are embedded in. Radio waves from distant sources get refracted and rotated by the interstellar magnetic field in ways that can be measured. The large-scale direction of the interstellar magnetic field in our galactic neighborhood had been estimated from all these indirect measurements, and those estimates said the field should be running at a substantial angle to the solar magnetic field, not the near-parallel alignment that Voyager found. Either the global estimates were wrong, or the heliosphere was bending the field lines around it locally, dragging them into alignment as the interstellar medium flows around the obstacle of the heliosphere. Most scientists now believe both factors contribute. The global estimates had real uncertainty built in, and the heliosphere does distort the local field. But the degree of distortion required to explain the Voyager data is larger than any model had predicted. And that means the heliosphere's influence on the surrounding interstellar medium is more significant than anyone had thought. Think of it this way: the heliosphere is like a rock in a river. The water flows around the rock, bending its path to accommodate the obstacle. If you measured the water flow right next to the rock, you'd find it running mostly parallel to the rock's surface, regardless of where the flow was headed before it hit the obstacle. The heliosphere does the same thing to the interstellar magnetic field. It bends the field lines around itself, but the calculations showed the rock, in our case, was doing more bending than its size should allow. The heliosphere was distorting the interstellar field more than the models said it could, which meant the heliosphere was stronger, or the field was weaker, or both, compared to what the models assumed. Every answer to a Voyager puzzle opened new questions. And the most consequential question the magnetic field non-rotation opened was about the shape of the heliosphere itself. A question that would only get stranger as more data came in. The question of the heliosphere's shape had been settled, in theory, long before Voyager crossed the heliopause. The standard answer was the comet. You've seen the diagram, the heliosphere as an elongated teardrop, with the rounded nose pointing in the direction the solar system is traveling through the interstellar medium, and a long tail, called the heliotail, extending in the opposite direction. The tail was supposed to extend far downstream, possibly hundreds of astronomical units, pulled out by the interaction between the solar wind and the interstellar flow, the same way a comet's tail is pulled away from the star's direction by the solar wind itself. The comet shape was physically reasonable. It was the expected result of a bubble of pressure moving through a medium, with the upstream side compressed and the downstream side stretched. Every simulation produced a version of it. Every textbook reproduced it. It was so well established that it had stopped being a prediction and had become an assumption, the starting point for calculations, rather than a result that needed verification. The magnetic field data from the heliopause crossing was the first hint that this assumption might be wrong. If the interstellar field runs mostly parallel to the heliopause boundary, as the Voyager data suggested, rather than at a steep angle to the heliosphere's motion, then the field doesn't drape around the heliosphere in the way that produces a comet tail. Instead, the field lines slide along the heliosphere's surface, and the magnetic pressure squeezes the heliosphere from the sides, rather than pulling a long tail downstream. Some theoretical models, fed the Voyager field directions, produced a heliosphere that was more rounded than a comet, with two shorter lobes extending backward rather than one long tail. The shape resembled a croissant more than a teardrop. If the heliosphere is a croissant rather than a comet, then everything drawn in every textbook about the shape of our solar system's bubble in the galaxy is wrong. More than wrong, it is a fundamentally different geometry, with different implications for how cosmic rays enter, how the heliosphere moves through regions of different interstellar density, and what future missions into the heliotail region would find. The debate between the comet and the croissant models has not been resolved. Both probes are traveling through the nose region of the heliosphere, sampling the rounded forward face, but not the tail. What the tail actually looks like, whether long and cometary, or short and wide, or something else entirely, remains unknown. This uncertainty about the shape of our own solar system's boundary in the galaxy was not the kind of uncertainty that was expected at this point in human exploration. By 2012, we had mapped the surface of Mars in detail, landed probes on Saturn's moon Titan, and photographed dwarf planets at the edge of the solar system. But the basic shape of the heliosphere, the bubble that contains everything we have ever directly explored, was still an open question. And the most definitive data we had on it came from two probes that were measuring it only at a single point each, sampling two tiny windows in a boundary that spans billions of miles. The scale of what was unknown, the scope of what the Voyager data had revealed about our own ignorance, was itself one of the mission's most important results. It wasn't just that the models were wrong, it was that the models had been wrong in ways we hadn't detected, because no instrument had ever been positioned to test them from close range. The boundary of the solar system was, until Voyager got there, entirely a product of imagination. However disciplined and mathematically rigorous that imagination was, Voyager arrived. The imagination met reality, and reality won. There was one more wrinkle in the magnetic field story from the heliosheath that deserves attention before moving to the heliopause crossing itself, because it fundamentally changed how scientists understood the energy budget of the outer heliosphere. The pickup ions that had stolen the proton heating energy at the termination shock continued to play a strange role deeper in the heliosheath. As these ions were swept outward with the solar wind, they created pressure waves and instabilities in the plasma, transferring energy to the ambient plasma through wave-particle interactions. The heliosheath was not a passive medium just holding material between two boundaries. It was alive with energy transfer processes that hadn't been included in the pre-Voyager models. The cosmic ray measurements in the heliosheath added another dimension to this energy story. Both Voyager probes measured anomalous cosmic rays throughout the heliosheath, bouncing back and forth in the magnetic field, gaining small increments of energy with each reflection. These particles were products of the heliosphere itself, born from pickup ions that had been accelerated to high energies. Their presence throughout the heliosheath confirmed that the region was not a quiet buffer zone but an active particle accelerator, processing material from the interstellar medium and returning it to the heliosphere as high-energy radiation. Understanding the exact mechanisms of this acceleration, how much energy was flowing through these processes, and what the implications were for the broader heliosphere, remained active research questions throughout the entire Voyager mission. The stagnation region, when Voyager 1 finally entered it around 2010, brought all these threads together in a way that was simultaneously elegant and frustrating. Elegant because the data painted a coherent physical picture. The solar wind stopped, the magnetic field piled up, the cosmic rays surged, and the heliosphere sat at the edge of its own boundary, straining against the interstellar pressure. Frustrating because the probe was right at the most interesting place in all of heliospheric science, the zone where two different astrophysical environments met and contested each other, and yet the crossing of the formal boundary was still months away. The data was extraordinary, The boundary was tantalizingly close, and the most important measurement of the entire mission was still ahead. The confirmation of the heliopause crossing was one of the cleanest pieces of detective work in the history of planetary science. No single instrument had directly screamed "boundary crossed." The plasma instrument that would have given the most direct measurement had been dead since 1980. The magnetic field hadn't rotated the way it should have. The particle data had been changing for months before the crossing and continued changing for months after. There was no obvious line in the data where one side was clearly the heliosheath and the other side was clearly interstellar space. What resolved the question was a ripple from the star itself. In March 2012, the star fired off a powerful coronal mass ejection, a massive eruption of magnetized plasma from its surface. These eruptions are common during active periods of the star's 11-year activity cycle. They travel outward through the heliosphere, faster than the usual solar wind, compressing the solar wind ahead of them and sending a pressure pulse racing outward through the heliosphere at speeds of several hundred miles per second. The March 2012 eruption was a large one. As it traveled outward, it carried with it a wave of enhanced magnetic field and increased plasma density, a disturbance in the solar wind that propagated outward like a ripple in a pond. That ripple reached the location of Voyager 1-inch April 2013. When it hit the local plasma, it set the electrons vibrating. This is called electron plasma oscillation, and it happens when a disturbance disturbs the local equilibrium of a plasma, causing the electrons to oscillate back and forth around their equilibrium positions at a frequency that depends precisely on how many electrons are there. The denser the plasma, the higher the frequency. The more rarefied the plasma, the lower the frequency. The plasma wave instrument on Voyager 1, which had been detecting electromagnetic waves throughout the mission, heard the vibration. The frequency of the oscillation gave scientists a number. The local electron density was roughly 0.05 of an electron per cubic centimeter. In the heliosheath at comparable distances from the star, the electron density is far lower, because the heliosheath is an extremely thin plasma of expanding solar wind. But 0.05 of an electron per cubic centimeter is consistent with the interstellar medium in the local interstellar cloud, the region of the galaxy our solar system currently occupies. Voyager 1 was in the interstellar medium. The August 25, 2012 date was confirmed by working backward from the timing. The pulse left the star in March 2012, traveled outward for over a year, and hit Voyager 1 at a distance consistent with its known position if it had been in the denser interstellar plasma since August 2012. The confirmation came not from a live detection, but from retrospective analysis. Humanity's first crossing of the heliopause was identified not in real time, but by reasoning backward from evidence that arrived 14 months later. The boundary had been crossed silently, unannounced, without fanfare, and scientists had to piece together the proof like detectives reconstructing a scene from indirect clues. Alongside the density confirmation, the particle data told a sharp, clean story that left no room for ambiguity. Two separate populations of energetic particles behaved in exactly opposite ways at the boundary, and their behavior was exactly what theory had predicted the heliopause should produce. The first population was anomalous cosmic rays. These particles had been observed throughout the heliosphere since they were first measured by early instruments in the inner solar system. They are energetic particles, more energetic than the solar wind, but less energetic than the most powerful galactic cosmic rays. Their origin was thought to be inside the heliosphere, pickup ions that had been accelerated, first at the termination shock, and then through wave-particle interactions in the heliosheath, until they reached cosmic ray energies. Since they were born inside the heliosphere, they should stay inside the heliosphere. The heliopause should be a wall that contains them. That is exactly what happened. At the heliopause crossing, anomalous cosmic rays dropped to essentially zero, from substantial abundances inside the heliosphere to near zero outside. The drop was dramatic and clean. The heliopause was an effective cage for these particles. The second population was galactic cosmic rays. These are the high-energy particles from elsewhere in the galaxy, the ones generated by supernova explosions and other violent astrophysical events and traveling through interstellar space for millions of years before arriving at our solar system. The heliosphere partially blocks them, especially at lower energies, because the solar wind's magnetic field can deflect them back outward. Inside the heliosphere, the galactic cosmic ray count is depressed relative to the true interstellar level. Outside the heliopause, the deflection is gone. At the heliopause crossing, galactic cosmic rays surged. The count jumped sharply and held at its new, higher level. Voyager 1 was outside the shield. The galaxy was fully present. The two populations, simultaneous and opposite responses at the same boundary, created one of the most definitive signatures in the entire mission dataset. One goes up while the other goes down, at precisely the same point in space, in exactly the way theory predicted they should respond to the heliopause. Even without the density measurement from the plasma oscillations, the particle data alone was telling a consistent and convincing story. This was the edge, and the probe had crossed it. 6 years later, the second probe reached the same boundary. Voyager 2 crossed the heliopause on November 5, 2018, at roughly 119 astronomical units from the star. This was slightly closer than Voyager 1's crossing at roughly 121 astronomical units. Another small asymmetry, another data point confirming that the heliosphere is not a sphere, and this crossing brought something that Voyager 1's crossing had not: a functioning plasma science instrument. Voyager 1's plasma instrument had failed in 1980, long before any of these measurements became relevant. For the first 3 decades of the interstellar mission, scientists had been measuring the plasma environment indirectly through the oscillation measurements and through the particle and field data that could be used to infer plasma properties. Direct measurement had been off the table since the failure. Voyager 2's plasma instrument, by contrast, had survived. When Voyager 2 crossed the heliopause, its plasma instrument was operational and measuring directly. The direct plasma measurements confirmed several things and complicated several others. The boundary's location was confirmed by a clear jump in the plasma density and temperature recorded directly by the plasma instrument. On one side of the crossing, the plasma properties matched the hot, rarefied solar wind of the heliosheath. On the other side, they matched the denser interstellar medium. The transition was real, measurable, and direct. The first complication was the thickness. The transition zone between heliosheath plasma and interstellar plasma was narrow in a way that was striking given the scale of what it was separating. The heliopause is the boundary between an entire stellar system and the rest of the galaxy. It separates a region that extends billions of miles from its center from the galaxy at large, and the transition zone was only a few 100,000 miles thick. Set against the 11 billion miles between the star and the heliopause, that thinness is remarkable. It is like the skin of a bubble, vanishingly thin compared to the volume it encloses. Models had predicted a thicker transition zone. They expected a more gradual mixing of plasma types across the boundary, a wider region of transition rather than a nearly instantaneous jump. The data said otherwise. The boundary was sharp, the transition was rapid, and the heliosphere's edge was far less diffuse than the models had suggested. The second complication was the dynamics. Voyager 2 didn't just cross the heliopause once and stay outside. Over the course of several days following the initial crossing, the probe crossed back into the heliosphere, then out again, then in again, before finally staying in the interstellar medium for good. The heliopause was moving. It was oscillating back and forth, driven by fluctuations in the solar wind's pressure on the inside and the interstellar medium's pressure on the outside. When a burst of solar wind activity increased the pressure from inside, the heliopause pushed outward, and the probe found itself back in the heliosheath. When the pressure ebbed, the heliopause retreated inward past the probe again. The heliopause was breathing. It was not a fixed wall at a fixed distance. It was a dynamic, oscillating boundary whose position shifted by millions of miles over the course of days, driven by the variable output of the star it enclosed. Scientists had theorized that this kind of motion was possible based on pressure balance arguments, but seeing it directly, watching the probe flicker in and out of the heliosphere like someone standing in a doorway while the door swings back and forth, was a vivid confirmation that the solar boundary is alive in a way that the static diagrams in textbooks could never convey. The oscillating heliopause also had a practical implication for the Voyager 2 data. The probe was sampling the boundary region multiple times from both sides, giving scientists a detailed look at the transition zone that they couldn't have gotten from a single clean crossing. Each time the probe crossed and recrossed, the instruments measured the plasma properties from new angles, building up a more complete picture of the transition than would have been available from a single transit. The plasma temperature outside the heliopause was the third complication, and the most significant scientifically. The plasma outside the heliopause was hot, hotter than the models predicted it should be. The region of the galaxy our solar system currently moves through is part of a large, low-density bubble called the local bubble, a region carved out by supernova explosions over the past several million years. The local bubble contains relatively warm plasma by the standards of dense molecular cloud regions, but by the standards of interstellar space generally, it is supposed to be a quiet, relatively cool region. Models of the local bubble and the local interstellar cloud within it had produced specific temperature estimates for the plasma near our heliosphere. Voyager 2's plasma instrument measured temperatures significantly higher than those estimates. The discrepancy wasn't trivial. The measured temperature was more than twice what some models expected. Something was heating the interstellar plasma in the immediate vicinity of our heliosphere at rates that the standard local bubble picture couldn't account for. Several mechanisms have been proposed. Charge exchange reactions between interstellar neutral atoms and solar wind protons that leak through the heliopause could deposit energy into the local interstellar plasma. Wave heating driven by instabilities at the heliopause could raise the temperature of the plasma just outside the boundary. The interaction between the heliosphere and the interstellar medium might itself be a source of plasma heating through mechanisms that the models hadn't fully included. None of these explanations has been definitively confirmed. The temperature discrepancy remains an open question in heliospheric science. It is a number in the data that doesn't match the number in any existing model, and the gap between them is large enough to represent a genuine gap in understanding, far beyond any small calibration issue. Just outside the heliopause, Voyager 2 also found evidence for a feature that models had predicted but that had never been directly sampled: the hydrogen wall. This is a region where interstellar neutral hydrogen atoms, drifting inward through space, pile up against the outer surface of the heliopause. The neutral atoms approach from the interstellar medium but can't cross the heliopause cleanly because charge exchange reactions near the boundary slow them down and heat them. The result is a slightly denser, slightly cooler layer of neutral hydrogen pressed against the outside of the heliopause like a cushion. The hydrogen wall had been inferred from observations of nearby stars, which showed similar features in their own astrospheres. Voyager 2's instruments directly sampled material consistent with a hydrogen wall for the first time, adding another indirect prediction to the list of things the Voyager data had confirmed or complicated. The magnetic field at Voyager 2's crossing told the same story as at Voyager 1's crossing. Almost no rotation. The field direction outside the heliopause was close to the field direction inside. Two crossings, 6 years apart, in different sectors of the heliosphere boundary, and both showed the same near parallel alignment between the solar and interstellar magnetic fields. The non-rotation was not an artifact of Voyager 1's broken plasma instrument or some quirk of the specific location Voyager 1 had sampled. It was a real feature of the heliopause boundary, confirmed by both probes independently. The interstellar magnetic field in our local galactic neighborhood is aligned nearly parallel to the solar magnetic field at the heliopause, and that alignment is not what any pre-Voyager model had predicted. The implications of this field alignment extended well beyond the heliopause itself. The direction of the interstellar magnetic field at the heliopause boundary is one of the key inputs to models of the heliosphere's overall shape. Specifically, it determines how the field lines drape around the heliosphere as the solar system moves through the interstellar medium, and those field lines exert magnetic pressure on the heliosphere that influences its geometry. The two Voyager measurements, by showing that the field runs nearly parallel to the heliopause surface rather than at a steep angle to it, forced a fundamental revision of what the heliosphere's shape should look like. For decades, the standard model was the comet. The heliosphere was an elongated teardrop shape, with the rounded nose facing into the direction of the solar system's motion through the interstellar medium, and a long tail, the heliotail, extending hundreds of astronomical units downstream. This was the shape that all the simulations produced, the shape in every diagram, the shape that was described in every review article. The Voyager field data, combined with other measurements from satellites inside the heliosphere, challenged this picture seriously. A comet shape requires a magnetic field that runs at a significant angle to the heliosphere's direction of motion, so that the field lines can wrap around the nose and trail downstream to form the tail. A field that runs nearly parallel to the heliopause surface, as the Voyager data suggested, doesn't produce a long comet tail. Instead, it squeezes the heliosphere from the sides, compressing it laterally and producing a shorter, wider, more rounded shape with two lobes curving backward rather than a single long tail pointing downstream. Some models generated after the Voyager results were analyzed, produced heliosphere shapes that look more like a croissant or a crescent than a comet. In these models, the heliotail exists, but is much shorter and wider than the traditional picture. The heliosphere's outline, if you could somehow view it from outside, would look like two rounded lobes pressed back against each other, very different from the aerodynamic teardrop in the standard diagrams. The debate between the comet and the croissant is ongoing. Neither Voyager probe is positioned to test the tail region directly. Both are traveling through the nose sector of the heliosphere, the forward-facing side that points into the interstellar wind. The tail region is directly opposite, and neither probe will ever be in a position to sample it. Resolving the shape question will require either remote sensing data of sufficient quality to image the heliosphere's outline from a distance, or a future mission that travels toward the tail rather than through the nose. In the meantime, the shape of our own solar system's bubble in the galaxy remains one of the most significant open questions in heliospheric science. Before the shape debate could be properly framed by the Voyager data, a separate satellite discovery had already shaken one of the most basic assumptions in the field. The bow shock, a feature that had appeared in heliosphere models for generations, was expected to form in the interstellar medium ahead of the heliosphere. As the solar system moves through the interstellar medium, the heliosphere pushes the surrounding gas and plasma out of the way. If the heliosphere is moving faster than the speed of sound in the local interstellar medium, this displacement creates a shock wave, a bow shock, ahead of the heliosphere, analogous to the shock wave that forms ahead of a supersonic aircraft. For a long time, models said the heliosphere was moving fast enough to produce a bow shock. The shock was drawn into every diagram, labeled in every textbook, described in every review article about the heliosphere. It was so well established as a feature that it had stopped being questioned. It was simply there, part of the structure, waiting to be confirmed by an eventual measurement. In 2012, the Interstellar Boundary Explorer satellite, known as IBEX, provided data that allowed scientists to re-examine the heliosphere's speed relative to the local interstellar medium. The result was surprising. The heliosphere was moving through the interstellar medium more slowly than previously thought, and the interstellar magnetic field was stronger than previous estimates had assumed. The combination of these two corrections changed the math significantly. A slower heliosphere in a stronger magnetic field might not be moving faster than the effective sound speed in that medium. If the flow were subsonic, there would be no bow shock. The shock that had been in every textbook for decades might simply not exist. Further analysis confirmed the finding. The bow shock was gone, not just undetected, theoretically excluded by the updated measurements of the heliosphere's speed and the interstellar field strength. The solar system doesn't create a shock wave as it plows through the interstellar medium. It creates a more gradual disturbance, a wave rather than a shock. The bow shock had been a feature of models for so long that its elimination felt like tearing a page out of a textbook that had been used for 30 years. And then, from the same IBEX satellite, came something that nobody had predicted at all. IBEX was launched in 2008 into a highly elliptical orbit around Earth, reaching a maximum distance of about 200,000 miles before swinging back close. From this orbit, it was positioned to detect particles coming in from all directions outside Earth's own magnetosphere. Its instruments were designed to catch energetic neutral atoms, particles that began as solar wind protons deep inside the heliosphere, underwent charge exchange with neutral hydrogen atoms, became neutral themselves, and then traveled in straight lines across the heliosphere and out through the heliopause without being deflected by any magnetic field along the way. By detecting these neutrals and measuring which direction they came from, IBEX could build a map of the intensity of energetic particle activity at the heliosphere's boundary, as seen from inside. The first all-sky maps IBEX produced revealed something that stopped scientists in their tracks. There was a ribbon, a narrow, bright band of enhanced energetic neutral atom emission running across the sky in a roughly circular arc, about 20 degrees wide, cutting across the heliosphere's boundary in a pattern that appeared to align with the direction of the local interstellar magnetic field. The ribbon stood out clearly above the relatively uniform background emission from the rest of the heliosphere boundary. It was real, it was bright, and it was not predicted by any model that had existed before IBEX flew. Nothing in the theoretical framework for heliospheric science had produced a ribbon. No simulation had generated one. No analytic calculation had demanded one. The ribbon was entirely, completely unexpected. When the first IBEX maps were published in October 2009, the reaction in the heliophysics community was a mixture of excitement and bewilderment. The data was clean. The feature was unambiguous, but nobody knew what it meant. More than 15 years later, it still hasn't been definitively explained. Several competing models have been developed, and the leading contenders share a general idea. The ribbon forms in a region where the interstellar magnetic field runs perpendicular to the line of sight from the boundary to Earth, causing secondary neutral atoms that have been partially processed by the heliosphere to concentrate in that specific angular region. When a solar wind proton undergoes charge exchange to become a neutral atom, it can travel outward through the heliopause and into the interstellar medium. Once there, it can undergo another charge exchange with an interstellar proton, becoming an ion again and getting picked up by the interstellar magnetic field. If the field is perpendicular to the line of sight, these reionized atoms spend more time in the same angular location before being swept away, creating an enhanced density of material that eventually produces more neutral atoms heading back toward Earth. The IBEX instrument detects those returning neutrals, and in the region where the field is perpendicular, it detects a bright band. This explanation works in principle, but the details don't all fit cleanly. The ribbon is brighter and narrower than even the best versions of this model predict. Some scientists favor alternative mechanisms involving waves in the interstellar plasma near the heliopause, or effects from the heliosphere's motion through the interstellar medium that concentrate particles in specific directions. The disagreement isn't about whether the ribbon exists, everyone agrees it exists, but about which physical process produces it. The ribbon is a test case for theories of the heliosphere-interstellar medium interaction, and no theory has yet passed the test cleanly. What the ribbon did do, regardless of its explanation, was shift the discussion about the heliosphere's shape. If the ribbon is aligned with the interstellar magnetic field, then its location on the sky tells you something about the direction the field runs. The ribbon's orientation in the IBEX maps was consistent with the Voyager magnetic field measurements, showing a field running nearly parallel to the heliopore's surface. The two independent measurements, one from inside the heliosphere using neutral atom imaging, and one from outside the heliosphere using direct magnetic field measurement, pointed in the same direction. The interstellar magnetic field in our neighborhood was running roughly parallel to the plane of the galactic disk, aligned in a way that would compress the heliosphere laterally and reduce the length of any downstream tail. The IBEX ribbon discovery, coming just 3 years before Voyager 1's heliopore's crossing, reframed the questions that the crossing data would need to answer. And the crossing data, when it came, raised new questions in turn. Each piece of the puzzle seemed to connect to every other piece, and none of them fit together into a clean, simple, final picture. The heliosphere was turning out to be a system of interlocking complexities, each boundary and region affecting the others, each measurement revealing new structure that hadn't been anticipated. The anomalous cosmic ray question, which had seemed like it might be settled by the heliopore's crossing, turned out to be more complicated than the crossing data resolved. Before the Voyager probes reached the termination shock, scientists had a clean theoretical picture of where anomalous cosmic rays came from. They were pickup ions, neutral atoms that had drifted into the heliosphere from the interstellar medium, gotten ionized, gotten swept up by the solar wind, and eventually been accelerated to high energies at the termination shock. The termination shock was the accelerator, doing its work at the outer boundary where the solar wind slowed to subsonic speeds, and the anomalous cosmic rays were the product, high-energy particles that filled the heliosphere as evidence of the acceleration happening at its outer edge. When Voyager 1 crossed the termination shock in 2004, the anomalous cosmic rays didn't peak at the shock, as they should have if the shock were the primary accelerator. The intensity peaked farther in, deeper in the heliosheath. The termination shock was doing some acceleration, but it wasn't doing enough to account for the full population of anomalous cosmic rays filling the heliosphere. Something else was contributing. Two main alternatives emerged. One focused on the geometry of the termination shock. Voyager 1 crossed the termination shock at a specific angle, and the shock is not geometrically the same at every point. Near the nose of the heliosphere, where Voyager crossed, the magnetic field geometry at the shock was less favorable for particle acceleration than at the shock's flanks, where the field runs at different angles to the shock surface. Particles accelerated at the flanks could then diffuse throughout the heliosphere, making the anomalous cosmic ray population appear to peak deeper in the heliosheath, even though the primary acceleration was happening far away. The second alternative pointed to magnetic reconnection events throughout the heliosheath as an additional source of acceleration, giving particles energy through the explosive release of magnetic energy when opposing field lines snap together. Both mechanisms are probably real. The termination shock accelerates some anomalous cosmic rays at its flanks. Reconnection in the heliosheath adds more. The clean, simple picture of a single dominant accelerator had given way to a multi-component system, with the contribution of each component depending on conditions that varied with position, solar activity, and the specific properties of the interstellar medium at the heliosphere's location in the galaxy. The data that was supposed to confirm the theory had instead revealed that the theory was an oversimplification. This is the pattern that repeats throughout the Voyager story. Every time a prediction met a measurement, the measurement was more complicated than the prediction. The physical system was not wrong, exactly. The physics were real. The forces and fields and particles were behaving according to the laws of physics, just as the models said they should. But the models had been built on simplifying assumptions, and at the heliosphere's boundary, those assumptions all broke at once. The termination shock was there, but not doing what it should. The heliosheath was structured when it should have been smooth. The heliopause was thin and breathing when it should have been thick and steady. The magnetic field wasn't rotating when it should have rotated, and the temperature outside was wrong. What made all of this scientifically valuable, rather than merely frustrating, was that each broken prediction was a discovery. Each time the data didn't match the model, it meant the universe was doing something the model hadn't captured. And the question of what the universe was doing, what physical process accounted for the anomaly, was where new understanding was born. The magnetic foam was a discovery. The asymmetric termination shock was a discovery. The thin, breathing heliopause was a discovery. The non-rotating field was a discovery. The ribbon was a discovery. Every model failure was a window into something real that the models hadn't seen. And the most important measurements were still to come, from Voyager 2, which had crossed the heliopause with its plasma instrument working and was now sampling the interstellar medium directly, sending home data that the entire heliophysics community was waiting for. The data Voyager 2 was sending from the interstellar medium in the months and years after the 2018 crossing was a new category of information for humanity. No human instrument had ever directly sampled the plasma outside the heliosphere before. Everything scientists knew about the very local interstellar medium, the specific cloud of gas and plasma that our solar system currently moves through, called the local interstellar cloud, had come from remote observations, spectroscopy of nearby stars whose light had traveled through this cloud, analysis of how the interstellar medium interacted with the heliosphere, inferred from data collected inside the heliosphere, estimates and models built up from fragmentary evidence. Now, there was direct data from the source, and it was both confirming and complicating the remote sensing picture. The electron density outside the heliopause was roughly consistent with estimates for the local interstellar cloud. The neutral particle flux was in the expected range. The magnetic field direction, though problematic for the shape models, was at least consistent with the direction inferred from the ibex ribbon. But the temperature remained anomalously high, and the energetic particle environment outside the heliopause was more complex than expected. One of the most interesting findings from Voyager 2's interstellar medium data was the detection of energetic particles in the interstellar medium that didn't come from the heliosphere. Inside the heliosphere, the energetic particle environment is dominated by solar wind-related particles and the anomalous cosmic rays described earlier. Outside the heliopause, the anomalous cosmic rays disappeared, but the instruments detected populations of particles with intermediate energies, more energetic than the baseline interstellar plasma, but less energetic than the full galactic cosmic rays, that appeared to be accelerated locally in the interstellar medium itself or at the heliopause boundary from the outside. These intermediate energy particles suggest that the heliopause boundary is an active site of particle acceleration, processing material from both sides and generating energetic particles that populate both the heliosphere and the local interstellar medium. The boundary layer between the solar wind and the interstellar medium turns out to be one of the more physically interesting locations in our cosmic neighborhood, a site where two very different plasmas interact, compress against each other, accelerate particles through magnetic reconnection and wave damping, and exchange material through complex charge exchange reactions. What this means in practical terms is that the boundary of our solar system is not a quiet edge, but an active region, and understanding it requires understanding the full complex of physical processes at the interface itself, beyond simply cataloging the heliosphere on one side and the interstellar medium on the other. The models that treated the heliopause as a simple pressure boundary, separating two relatively passive fluids, were missing the physics that made the boundary interesting. Both Voyager probes were also detecting the interstellar medium's neutral particle component in ways that added detail to the picture of the local interstellar cloud. The interstellar medium contains neutral hydrogen, helium, and heavier elements, in addition to the ionized plasma. These neutral atoms can pass through the heliopause without being deflected by the magnetic field, so they drift into the heliosphere and can be detected even from inside, Instruments on both probes detected these neutrals throughout their traversal of the heliosheath and heliopause regions, and the data was used to constrain models of the neutral gas density and temperature in the local interstellar cloud. The picture that emerged was of a cloud with properties consistent with it, having been heated by nearby supernova explosions in the geological past. The local bubble, the larger structure that contains the local interstellar cloud, was carved out by a series of supernova explosions over the past few million years, and the hot, low-density plasma that fills the local bubble is the remnant of that explosive heating. The local interstellar cloud is a slightly denser condensation within this low-density bubble, and it has temperature and composition properties that reflect its history of exposure to the bubble's hot interior material. Our solar system has been passing through the local interstellar cloud for roughly 100,000 years, and it will continue doing so for another few thousand years before it exits into the lower density hot plasma of the local bubble proper. When that transition happens, the heliosphere will change significantly. Without the relatively denser cloud material pressing on it from outside, the heliosphere will expand outward to a new, larger equilibrium size. Fewer interstellar neutrals will drift inward through the heliosphere, changing the pickup ion population and the chemistry of the outer heliosphere. The exact timing of this transition and its implications for Earth's environment are subjects of ongoing research. The Voyager data from outside the heliopause is helping scientists understand what that transition will look like, because it's providing measurements of the local interstellar cloud properties from the very edge where the heliosphere meets it. Models of what happens when the heliosphere's external environment changes depend critically on accurate measurements of the current external environment, and the Voyager probes are the only sources of direct measurements of that environment available. This is why every instrument on both probes is precious. Every operational instrument is collecting data that can never be replicated, from a location that no other mission is scheduled to reach for decades. The data from Voyager 2's plasma instrument in the interstellar medium is unique in the history of human science. The magnetic field measurements from beyond the heliopause are irreplaceable. When these instruments eventually fail, the gaps in understanding they leave will be real and lasting, and the instruments are failing, one by one, as the power runs out. The power situation on both probes is the hidden clock ticking underneath every piece of science they produce. The radioisotope thermoelectric generators that power both probes were loaded with plutonium-238 before launch. Plutonium-238 has a half-life of about 87.7 years, meaning it loses about half of its heat-producing material over that period. At launch, each probe's generators produced around 470 watts of electricity. By the time both probes crossed the heliopause, the power output had dropped to something in the range of 250 to 260 watts, and it continues to fall by roughly 4 watts per year. Mission engineers managed this declining budget with extraordinary care. Over the decades, they have shut down instruments and subsystems in a carefully planned sequence, prioritizing the science instruments that provide the most unique data for last. Heaters that keep non-critical components warm in the extreme cold of deep space have been turned off, accepting the risk of component failure in exchange for keeping the critical instruments running. Software has been updated to run the computers more efficiently. Every available watt is allocated against a priority list, and as the list shrinks, the choices become harder. The result is that both probes carry fewer active instruments today than they did at launch, but the instruments that remain are the most important ones for the interstellar mission: the magnetometers, the cosmic ray subsystem, the low-energy charged particle instruments, and the plasma wave subsystem. On Voyager 2, the plasma science instrument still operates. On Voyager 1, it has been gone for over 4 decades, but the plasma wave instrument compensates partially by inferring plasma density from oscillation measurements. By the late 2020s, the power output will fall below what is needed to keep even the last science instruments operating. One by one, over the course of the following years, they will shut down. Not dramatically, not with any final transmission or closing ceremony, simply a lack of power, the last bit of heat from a lump of metal that has been cooling since 1977, no longer enough to drive the instrument that needs it. The mission will end the way most things in the universe end, not with an explosion, but with a quiet, dimming, a fading, a silence that arrives not all at once, but in small steps until there is nothing left to hear. After that silence, the probes will continue traveling, dark, cold, powerless, but still moving through the interstellar medium at their original velocities, carrying the golden records towards stars they will never reach on any timescale that means anything to human civilization. They will be the longest traveling human artifacts in history, and they will be entirely beyond any possibility of recovery or contact. Voyager 1 will pass within about 1.7 light-years of a small red star called Ross, 248 inches, roughly 40,000 years. By then, whatever has become of human civilization will have had 40,000 years to develop beyond anything we can currently imagine. The probe will be an archaeological artifact from a species that had just learned to send things beyond its own solar system. But before that silence comes, there is still more to learn, and the most dramatic chapter in the operational life of the Voyager mission was not the heliopause crossing. It was a crisis that nearly silenced Voyager, 1-inch 2023, and the extraordinary engineering response that brought it back. The story of anomalous cosmic rays was supposed to reach a clean resolution when the Voyager probes crossed the heliopause. The standard model said these particles were accelerated at the termination shock, filled the heliosphere, and should vanish at the heliopause because the heliopause would contain them inside. The first part of that prediction came true. Anomalous cosmic rays dropped sharply at the heliopause crossing of both probes. The heliopause was an effective containment boundary, but the question of where exactly in the heliosphere these particles were gaining their energy remained unresolved. The termination shock, which had been cast as the primary accelerator, had failed to show the particle intensity peak that models predicted. The peak was in the heliosheath, not at the shock itself. Years of analysis after the termination shock crossings generated two serious competing explanations. Acceleration at the flanks of the termination shock, where the magnetic geometry was more favorable, and acceleration throughout the heliosheath via magnetic reconnection. Both mechanisms are real, both contribute. Neither one alone accounts for the full population. What the heliopause crossing did definitively confirm was the containment. Anomalous cosmic rays live inside the heliosphere. They don't exist in significant amounts in the interstellar medium. This tells scientists something important. The processes that create them are entirely internal to the heliosphere. The termination shock, the heliosheath, the pickup ions, the magnetic foam, the reconnection events, all of these are feeding a particle population that exists only within the bounds of our solar system's magnetic bubble. Outside the heliopause, they are essentially absent. They are, in a very real sense, a product of our solar system's particular relationship with its surrounding interstellar environment. Understanding their source matters beyond the immediate physics. Anomalous cosmic rays carry information about the conditions at the heliosphere's outer boundaries, their energy spectrum, their composition, their spatial distribution within the heliosphere. All of these are fingerprints of the processes that created them. By reading those fingerprints, scientists can infer properties of the termination shock, the heliosheath, and the heliopause that can't always be measured directly. The anomalous cosmic rays are a distributed sensor network spread throughout the heliosphere, encoding information about the boundary regions in the particles themselves. That information has been used to refine models of the termination shock's acceleration efficiency, the heliosheath's magnetic structure, and the pickup ion population throughout the outer heliosphere. None of these models has achieved perfect agreement with the data. Each refinement brings better fit in some areas and reveals new discrepancies in others. The anomalous cosmic ray story is not closed. It is one of the continuing scientific threads that makes the Voyager mission a living investigation rather than a completed archive. One thread that the heliopause crossings did begin to close, at least partially, was the question of what the true galactic cosmic ray spectrum looks like. From inside the heliosphere, the galactic cosmic ray spectrum has always been observed in a filtered form. The solar wind's magnetic field deflects lower energy cosmic rays, preventing them from penetrating deeply into the heliosphere. The filtering effect is strongest for particles with energies below a few 100 million electron volts, and it varies with the solar activity cycle. More filtering during periods of high solar activity, when the solar wind is stronger and more magnetized, and less filtering during solar minimum. But even during solar minimum, the low energy end of the galactic cosmic ray spectrum is significantly suppressed inside the heliosphere compared to what exists in the interstellar medium. Both Voyager probes, now operating in the interstellar medium, have measured the unfiltered spectrum directly for the first time in the history of space science. The difference between the filtered spectrum measured inside the heliosphere and the unfiltered spectrum measured outside is significant at low energies. There are more low-energy cosmic rays in the galaxy than decades of measurements from inside the heliosphere had shown. The heliosphere had been hiding them, filtering them out before they could reach Earth-based or near-Earth instruments. This matters in multiple ways. Galactic cosmic rays are a major scientific concern beyond their inherent interest. They are a source of energy for the interstellar medium. When a cosmic ray travels through interstellar gas, it deposits energy through ionization, knocking electrons off atoms and heating the gas slightly. Over time, across enormous volumes of space, cosmic rays contribute significantly to the energy budget of the interstellar medium. They affect how gas clouds cool and collapse to form new stars. They influence the chemical reactions that produce complex molecules in the interstellar medium. They partially drive the magnetic field structure of the galaxy by energizing plasma and driving currents. All models of these processes were calibrated on cosmic ray spectra measured from inside the heliosphere, which means they were calibrated on a filtered version of the true spectrum. The low energy contribution had been underestimated. Every calculation that used the cosmic ray energy input to the interstellar medium needed to be revised upward, particularly at the low energy end. The implications ripple outward into models of star formation, of the interstellar medium's thermal structure, of the galaxy's magnetic evolution. A measurement made 15 billion miles from Earth, in the very local interstellar medium just outside our own solar system, had consequences for how scientists model the evolution of the Milky Way galaxy. This is the scale at which the Voyager mission operates when you follow the implications to their conclusions. The probes were designed to explore the outer planets. They exceeded that mission entirely, and the scientific legacy they are still building, more than 4 decades into the interstellar phase, reaches from the specific physics of the heliopause to the global physics of galactic evolution. The heliosphere's role as a shield is one of the most important aspects of its scientific significance, particularly in the context of life on Earth. The cosmic ray shielding that the heliosphere provides is not trivial. Without the heliosphere, the flux of low-energy galactic cosmic rays reaching Earth's surface would be significantly higher than it currently is. The atmosphere provides additional shielding against cosmic rays, but the heliosphere is the first line of defense, turning away the lowest energy particles before they ever get close. At higher energies, cosmic rays penetrate both the heliosphere and the atmosphere and reach the ground, creating secondary particle showers when they collide with atmospheric atoms. These secondary particles are the cosmic rays that ground-based detectors measure, and they are part of the natural radiation environment that life on Earth has always experienced. But at low energies, the heliosphere is an effective shield, and without it, that natural radiation background would be higher. Whether the difference in cosmic ray flux would be biologically significant is debated. The heliosphere's shielding is most effective at the lowest energies, and low-energy cosmic rays produce less damaging secondary radiation than higher-energy primaries. But over geological timescales, even small changes in the cosmic ray environment can affect mutation rates, DNA damage repair mechanisms, and evolutionary pressures. There is geological evidence suggesting that periods of higher cosmic ray exposure, recorded in isotope ratios in ancient ice cores and in certain rock formations, correlate with periods of reduced heliospheric shielding. The exact biological significance of these variations is still debated. The Voyager data on the unshielded cosmic ray spectrum allows scientists to calculate, more precisely than before, exactly how much shielding the heliosphere currently provides. And because the heliosphere's size depends on the solar wind output, which varies with the star's activity cycle and with the properties of the interstellar medium it's moving through, the shielding has changed over Earth's history and will continue to change. When the solar system was moving through a denser region of the interstellar medium millions of years ago, the heliosphere may have been compressed to a fraction of its current size, providing far less shielding and exposing Earth to much higher cosmic ray fluxes. The Voyager data is becoming a cornerstone for calculations of these historical variations and their possible influence on life's evolution on our planet. The year 2023 brought the most dramatic operational crisis of the entire Voyager mission. Voyager 1, still the farthest human-made object and still operating in the interstellar medium, began sending back data that was wrong. The science data stream, which had been flowing cleanly for decades, started returning nonsense. The flight data system, the computer that packages data from all the scientific instruments and formats it for transmission to Earth, was producing garbled output. Instead of meaningful measurements from the instruments, the transmitted data was patterns of repeated values, corrupted sequences, information that bore no relationship to what the instruments were actually measuring. The probe was still alive. Engineers could see from the carrier signal that Voyager 1 was still receiving commands and responding normally. The spacecraft was functioning. The instruments were presumably operating, but the data was garbage, and if the problem couldn't be fixed, the science mission was effectively over. The challenge of diagnosing the problem was immense. Every command sent to Voyager 1 takes more than 22 hours to arrive. Because the signal travels at the speed of light across more than 15 billion miles, every response takes another 22 hours to come back. A single round-trip exchange takes nearly 2 days. Diagnostic commands that would take seconds to execute and confirm on a computer sitting in front of you take 2 days to execute and report on Voyager 1. A systematic diagnostic process that might involve dozens of steps could take months just in communication time. Setting aside the time needed to analyze responses and formulate the next question, engineers at NASA's Jet Propulsion Laboratory worked methodically through the problem. They sent commands that prompted Voyager 1 to report on its own internal state. They analyzed the patterns in the corrupted data for clues about which system was failing. They cross-referenced the corrupted outputs against known failure modes for the specific hardware that Voyager 1 carries. And eventually, after months of careful work and more than a few dead ends, they identified the source. A single memory chip inside the flight data system had become corrupted. The chip was responsible for storing part of the flight data system's operating code, and the corrupted memory was causing the code to execute incorrectly, producing garbage data instead of properly formatted science measurements. Memory corruption in space hardware is not unprecedented. Radiation damage accumulates in electronic components over time, and after nearly 50 years in space, Voyager 1 has been exposed to a lifetime's worth of high-energy particles, ultraviolet radiation, and other environmental insults that can alter the electrical properties of memory cells. The corrupted chip was the result of decades of operation in a hostile environment, and it was remarkable that the hardware had lasted as long as it had before failing. The solution the engineers devised was creative in the way that space engineering problems tend to require creativity, not by fixing what was broken, but by working around it. The operating code that resided in the corrupted memory section was relocated. The code was split up and distributed across several healthy sections of the flight data system's memory, sections that didn't contain any critical data at the time and that the corrupted chip hadn't affected. Since the memory sections were of different sizes, the relocation required careful engineering to ensure the code would still execute correctly when spread across non-contiguous blocks of memory. The patch was developed, tested on Earth using a flight system simulator, and transmitted to Voyager 1-inch sections over several weeks. Each section of the patch was sent, confirmed, received, and then the effects were monitored over the following days. In April 2024, the effort succeeded. The science data returned. The garbled stream cleared up. The instruments started sending real measurements again. Voyager 1 was back. The engineering achievement was extraordinary by any measure. A team of scientists and engineers, using a computer architecture that is essentially obsolete on Earth and manuals written in the 1970s, successfully repaired a broken memory system on a spacecraft more than 15 billion miles away, communicating through a radio link that imposed a 4-hour delay on every round-trip exchange. The repair took months of careful, patient work, and it succeeded. The mission continued. The 2023-2024 crisis highlighted something that is both inspiring and sobering about the Voyager mission: its fragility. Two spacecraft from the 1970s, running on systems that were designed to last 5 years, are still operating after nearly 50 years. The engineering margin that made this longevity possible was built in deliberately by engineers who understood that a mission to the outer solar system needed more robustness than a typical mission. But that robustness has a limit. Each year that passes, each instrument that fails, each watt that the generators lose, brings both probes closer to the silence that is eventually unavoidable. The power math is relentless. The generators lose roughly 4 watts of electrical output per year. The instruments need a minimum amount of power to operate. When the power drops below that minimum, the instrument shuts down. By the late 2020s, the power budgets of both probes will be tight enough that the last science instruments will need to be shut down. The exact timing depends on the specific power requirements of each instrument and on how the power management is prioritized. But the end of the scientific mission is within this decade, and probably within the next few years. When the last instrument goes dark, the Voyager probes will continue to exist as physical objects, moving through interstellar space at their original velocities. They will carry the golden records and the engineering legacy of the people who built them. They will be dark and cold and completely beyond any possibility of human contact, but they will still be there, crossing the interstellar medium, slowly approaching the gravitational boundary of the local interstellar cloud, eventually passing through a region where the star's gravity is so weak as to be negligible. The interstellar medium that both probes are sampling right now is not what scientists expected it to be. The local interstellar medium near our heliosphere has structure. It has regions of different density, different temperature, different particle populations. The plasma detected by Voyager 2's instruments is not the uniform, passive background that textbook descriptions implied. It varies with position. It has features. It has energetic particles from multiple sources. It has a temperature that doesn't match the standard model. Voyager 1 and Voyager 2 are sampling this medium at 2 specific points, in 2 specific directions from the star. And even from those 2 points, the data shows variability that suggests the interstellar medium has structure on scales that the 2 probe separation can resolve. The interstellar medium in our corner of the galaxy is not the same in every direction. It has a texture, a grain, features that reflect the history of the region, the ancient supernova explosions that carved the local bubble, the currents and turbulence in the interstellar plasma, the interaction between the medium and the heliosphere itself. Both probes are building up a time series of measurements from their respective positions, and that time series is revealing variations that wouldn't be visible from a single snapshot. The interstellar medium changes over time. Density fluctuations propagate through it. Waves and turbulence move through the plasma on timescales of days to months. The magnetic field varies. The energetic particle flux varies. The heliosphere responds to these variations by shifting its boundaries, and both probes, sitting just outside the heliopause, can detect both the interstellar variations and the heliospheric responses they trigger. The scientific value of this time series will only increase as the dataset grows longer. A measurement taken over years allows scientists to distinguish between short-term variability and long-term trends, to identify periodic signals, to correlate changes in the interstellar medium with changes in the heliosphere's boundaries. Every year, the probes keep operating is another year of this unique data. Every instrument shutdown is an irreplaceable loss. The legacy of the Voyager probes for the study of other stellar systems is significant and growing. Every star with a meaningful stellar wind creates its own version of the heliosphere, a bubble of stellar wind plasma, bounded by a heliopause equivalent boundary, embedded in whatever interstellar medium the star is moving through. These stellar astrospheres have been detected around a handful of nearby stars through remote sensing techniques, mostly by observing the interaction between the stellar wind and the interstellar medium in ultraviolet light. But the properties of these astrospheres have always had to be modeled based on parameters derived from studies of our own heliosphere. Before the Voyager probes reached the heliopause, those models were built on a heliosphere that physicists thought they understood. The termination shock was where the models said it should be, roughly. The heliopause was at the distance the models predicted, roughly. The heliosheath had the general properties the models described. The whole picture was approximately right. After the Voyager data came in, the picture was revised in almost every detail. The termination shock was asymmetric. The heliosheath was filled with magnetic foam. The heliopause was thin and dynamic. The field direction was nearly parallel. The temperature outside was too high. The shape was uncertain. All of these revisions changed the calibration of models used to study astrospheres around other stars. If our heliosphere's termination shock is asymmetric because of the interstellar magnetic field's pressure, then other stars' termination shocks are probably also asymmetric, in ways that depend on the interstellar magnetic field in their specific galactic locations. If our heliopause breathes and oscillates in response to stellar wind variations, then other stars' astrospheres do the same, with the amplitude of oscillation depending on the variability of those stars' winds. If the magnetic field at the heliopause is more parallel than perpendicular to the boundary, and this affects the heliosphere's shape in the ways the models suggest, then the shapes of other stellar astrospheres are also probably not the textbook comet shapes, but something more complex. These revisions matter for astrobiology. The size and effectiveness of a star's astrosphere determines how much of the interstellar medium's cosmic ray flux reaches that star's planets. A star with a large, strong astrosphere shields its planets more effectively than a star with a small, weak one. A star moving through a dense region of the interstellar medium may have its astrosphere compressed enough that cosmic ray shielding is substantially reduced. A star in a region of the galaxy with particularly strong interstellar magnetic fields may have an astrosphere with a very different shape and a different shielding effectiveness than a star in our neighborhood. The question of cosmic ray shielding is relevant to the habitability of exoplanets. If a planet orbits a star whose astrosphere is too small or too weak to provide meaningful cosmic ray shielding, the planet's surface receives much higher cosmic ray fluxes. Whether this is fatal to life as we know it depends on factors that are not fully understood, but it is a variable that should be included in assessments of planetary habitability. The Voyager data, by giving scientists their first direct measurements of how a heliosphere actually works from the inside out, is improving those assessments. The golden records aboard both probes contain the most careful description of humanity that was possible to encode in 1977. Sounds, images, diagrams, music, greetings, a map of the solar system's location in the galaxy, derived from the timing patterns of known pulsars, so that any finder could work out where in space the probes originated. The records were created with the assumption that intelligent life elsewhere in the galaxy might someday encounter them. The probability of that happening, in any time frame relevant to human civilization, is effectively zero. But the records were not really about probability. They were about character, about what we chose to say when we had the chance to say something that would outlast everything else we've ever built. What the Voyager data has revealed about the address those records came from is more complicated and more interesting than the 1977 picture. The address is inside a bubble that isn't spherical. The bubble's edge is thinner than anyone expected, dynamic rather than fixed, and magnetically aligned in ways that no model predicted. The temperature outside the bubble doesn't match the standard model of the local galactic neighborhood. The shape of the bubble is still debated. A ribbon of emission wraps around the outside of it, and nobody can fully explain why. The star's solar wind isn't as dominant at the boundary as the models said, and the interstellar medium is more influential than the models allowed. The address is more complex than the message in the bottle knew when it was dropped into the cosmic ocean. Every model that was broken by the Voyager data represents real knowledge gained. The heliosphere is asymmetric. We know this now, directly, because two probes crossed the termination shock at different distances. The heliopause breathes. We know this directly, because one probe watched it oscillate. The magnetic field at the boundary is nearly parallel. We know this directly, because two magnetometers on two probes measured it in two different sectors. The temperature outside is high. We know this directly, because one plasma instrument sampled it. The bow shock doesn't exist. We know this because the measurements of the heliosphere's speed and the interstellar field strength rule it out. The ribbon is real. We know this because IBEX mapped it across the whole sky. Each of these is a fact about the universe that wasn't in any textbook before the probes arrived. Each of these facts forced a revision of physical models that had been built over decades by careful, talented scientists working from the best available data. The models were wrong because they hadn't been tested against reality at the heliosphere's boundary. Once tested, they were revised. That's how science works. And the revisions, in this case, were large enough that the boundary of our own solar system looked almost unrecognizable compared to the pre-Voyager picture. Both probes are still moving, still covering ground, roughly 40,000 miles per hour into the unknown. The last instruments are counting down to silence, but the data they've already sent home will be analyzed and reanalyzed for decades, generating new insights as new theoretical tools become available to interpret it. The Voyager dataset is more than a historical record of two spacecraft journeys. It is a scientific resource whose full value has not yet been extracted. When the silence finally comes, when both probes are beyond the reach of any radio dish on Earth, they will still be out there. Dark metal and gold-plated copper records, moving through a medium that turned out to be far stranger than anyone modeled, towards stars that are too far away to be considered destinations. What they leave behind, beyond the physics they revealed, is a proof of principle that a species with enough patience, enough engineering skill, and enough curiosity can reach the edge of its own home and look back, and that what it finds at the edge is not the boundary it drew on its maps, but something more complicated, more surprising, and more alive than the model ever was. We sent two machines to the edge of everything we knew. They found something that nobody predicted, and we are still learning what to make of it. The Oort cloud, the vast spherical shell of icy bodies that extends from roughly 2,000 astronomical units outward to perhaps a quarter of the distance to the nearest stellar neighbor, represents the outermost gravitational reach of the star at our solar system's center. It is not a region that has been directly explored, No spacecraft has reached the inner edge of the Oort cloud, and no space telescope has imaged individual Oort cloud objects because they are too small and too far away to detect with current instruments. The Oort cloud is inferred from the comets that occasionally fall inward from it, perturbed by gravitational interactions with passing stars or giant molecular clouds swooping through the inner solar system in trajectories that reveal their distant origins. Voyager 1 is currently about 163 astronomical units from the star. The inner edge of the Oort cloud is estimated to begin somewhere between 2,000 and 5,000 astronomical units out. At Voyager 1's current speed, it will take roughly 300 years just to reach the inner edge. Once inside the Oort cloud, the probe will spend about 30,000 years crossing through it. These are the timescales on which the Oort cloud operates, tens of thousands of years, far beyond the span of human history. None of these numbers are the probe's destination. The probe has no destination in any meaningful sense. It is simply moving in a fixed direction at a fixed speed, carrying no propulsion, capable of no navigation decisions. It will go where its initial trajectory points, forever, until the gravity of some passing star or the diffuse gravitational field of the galaxy itself deflects its path, which will also take thousands of years to become significant. What the Oort cloud represents, scientifically, is the outer limit of what can reasonably be called our solar system. The heliopause marks the outer limit of the solar wind. The Oort cloud marks the outer limit of the star's significant gravitational influence. In between, from about 121 astronomical units, where the Voyager probes currently are, to about 2,000 astronomical units or more, where the Oort cloud begins, there is a vast region of interstellar space that is gravitationally dominated by the star, but is otherwise essentially interstellar in character. The solar wind doesn't reach it, the heliosphere doesn't include it, but the comets that live there are gravitationally part of our solar system. Voyager 1 and Voyager 2 are in this middle zone, past the heliosphere, technically in interstellar space, in the sense that the solar wind no longer touches them, but still gravitationally bound to the star in the loose sense that they are nowhere near the edge of the star's gravitational reach. They are, in the most literal possible sense, between worlds. Not inside the solar system's magnetic bubble, not yet at the outer edge of its gravitational domain. This middle zone is scientifically interesting in ways that haven't been fully explored. The interstellar medium in this region is likely not the same as the interstellar medium farther out. The heliosphere's presence disturbs the local interstellar medium, creating a wake and a deflection pattern that should extend for some distance beyond the heliopause. The hydrogen wall, the pileup of neutral hydrogen against the heliopause, is one feature of this disturbed region. There may be others. As both Voyager probes travel farther from the heliopause, the data they collect can track how the influence of the heliosphere on the surrounding interstellar medium decreases with distance, building a picture of the full extent of the heliosphere's impact on its environment. This kind of measurement is unique. Remote sensing techniques can detect the influence of stellar astrospheres on the interstellar medium around other stars, but they can't resolve the detail that in situ measurements provide. Both Voyager probes, by sampling the interstellar medium at increasing distances from the heliopause, are providing the kind of detailed, position-by-position data that no remote sensing observation can replicate. The comparison with other stars is ultimately what gives the Voyager mission its broadest scientific significance. Our solar system is one of hundreds of billions in the Milky Way galaxy. Each of those star systems has its own stellar wind, its own version of the heliosphere, its own interaction with the surrounding interstellar medium. The properties of those interactions vary enormously, with the star's mass, age, and luminosity, with the local interstellar medium density and magnetic field, with the star's velocity relative to the interstellar medium, with the activity cycle of the star. Young stars, which tend to be more active and produce stronger stellar winds, may have astrospheres that extend much farther out than our heliosphere. Their strong winds compress the surrounding interstellar medium more aggressively and create larger, more powerful shielding bubbles. Older stars, particularly those in the late stages of their lives, produce weaker winds that may allow their heliospheres to shrink below what is needed to provide significant cosmic ray shielding. Stars moving through the dense gas clouds near the galaxy's spiral arms face external pressures that can compress their astrospheres dramatically, even if the stellar wind is strong. For any of these stellar systems, the question of what the astrosphere actually looks like and how well it shields the orbiting planets from galactic radiation depends on the same physical processes that Voyager has been studying for decades. The termination shock, the heliosheath, the heliopause, the interstellar magnetic field, all of these features exist in some form around every star with a meaningful stellar wind. The Voyager data provides the calibration against which models of those other astrospheres are checked. And because the Voyager data revised almost every pre-existing model in significant ways, the calibration it provides is more accurate and more physically realistic than what was available before. The question of which stars are most likely to have astrospheres capable of supporting life on their planets is one of the most interesting questions in astrobiology right now. The cosmic ray environment at a planet's surface depends critically on the astrosphere. A planet orbiting a star with a strong, well-established astrosphere is protected from low-energy galactic cosmic rays in the same way Earth is protected by the heliosphere. A planet without that protection experiences a harsher radiation environment, which may or may not be inimical to life, depending on the biology involved and the thickness of the planet's own atmosphere. What Voyager has taught us about our own heliosphere is that the protection it provides is less perfect and less stable than the simple models suggested. The heliosphere breathes, its boundaries move. The shielding it provides varies with solar activity, with the properties of the interstellar medium it moves through, and with the specific direction from which cosmic rays approach. The average level of protection is significant, but it is not a constant. Life on Earth has always lived with a variable cosmic ray background, and the variability is larger than the pre-Voyager models would have predicted. This variability is now a quantitative science. With the Voyager data in hand, scientists can calculate the average level of cosmic ray shielding that the heliosphere provides, as well as the range of variability and the physical processes that drive it. They can project that knowledge onto other stars and make more informed assessments of the radiation environments that planets around those stars might experience. They can identify stars that are most likely to provide stable, Earth-like shielding and stars that are likely to provide much more variable or much weaker protection. The mission that began with a planetary survey in 1977 has become, in its 5th decade of operation, a fundamental resource for the search for habitable worlds around other stars. The data flowing back from 15 billion miles away, barely detectable against the background noise of the universe, is contributing to questions that weren't asked in 1977 and can't be answered without what Voyager found. The 2 probes will go dark within this decade. The instruments will shut down one by one. The signals will weaken. The radio transmitters will eventually fail or run out of power. And then there will be silence on the frequencies that engineers have been listening to for nearly 50 years. After the silence, the probes continue, dark, cold, still, carrying everything they ever were, through interstellar space that is stranger than anyone who built them imagined, toward a future that is measured not in years but in geological ages, not in the lifetime of any person but in the lifetime of civilizations. The galaxy will continue to turn. Stars will continue to be born and die. The universe will continue to expand, and 2 small machines from a small planet around an unremarkable star will keep moving at about 38,000 miles per hour through the dark with the golden records and the data and the memory of the people who listened to them for so long. What we learned from them is that the edge of our home is stranger, more dynamic, more surprising, and more physically rich than any model we built before we went to look. What we learned is that the universe doesn't simplify when you approach it closely. It deepens. And what we learned is that the right response to a broken model is not frustration but curiosity, because every broken prediction is a doorway into something real that we didn't understand before. The probes broke every model we had, and every broken model taught us something true. The process of science at its best looks like this. You build the best model you can from available data. You design a test that can distinguish between your model and reality. You conduct the test, and you revise your model to fit the result. Voyager was that test for decades worth of heliospheric physics models, and the models failed the test in ways that were, in retrospect, humbling and instructive. Every boundary was more complex than drawn. Every transition was more dynamic than expected. Every prediction was an approximation that the universe improved upon. What the Voyager mission demonstrated, beyond everything it measured, is that physical systems at the boundaries between different environments are never simple. At the edge of the heliosphere, solar wind physics meets interstellar medium physics, and the meeting point generates processes that neither physics alone would predict. Magnetic foam that doesn't exist in either the undisturbed solar wind or the undisturbed interstellar medium. Anomalous cosmic rays that are a product of the interaction between the two regimes. A ribbon of energetic neutral atoms that encodes information about the interstellar magnetic field in a way that requires both the heliosphere and the interstellar medium to be present simultaneously. The boundary is its own distinct region, with its own physics, its own processes, its own phenomena. This lesson generalizes. Every boundary in the universe, between every pair of interacting environments, is probably richer than the models built from studying either environment in isolation. The lessons of the heliopause apply to the boundaries between planetary magnetospheres and solar winds, to the interfaces between stellar winds and planetary atmospheres, to the regions where galactic disks meet the intergalactic medium. The boundary is where the interesting physics lives. Voyager went to the boundary of our solar system and confirmed this principle in the most direct way possible. 2 probes, 50 years, 15 billion miles, and the universe, at the edge of everything we knew, was stranger than the map said it would be, which is, when you think